first fundamental theorem of calculus. Our second fundamental theorem of calculus, or basically like the second part of your fundamental theorem of calculus, deals with what we call accumulation functions. And accumulation functions are still an integral. So what does the integral of f of x dx represent? Okay, yes, the antiderivative, but what does it represent like pictorially?
Oh, the area under the curve.
Okay, so our integral represents the area under the curve. And so usually we go from A to B. And what an accumulation function does is says, okay, I don't just want one area. I want you to now create a function that accumulates or adds up a whole bunch of different areas. So instead of there being a top bound, this top bound becomes a variable. Because now I'm looking at the area from 0 to 1, and then 0 to 2, and 0 to 4, and I can continue going and adding on additional areas. It's accumulating area. Now, what the second fundamental theorem of calculus helps us to talk about is if I have one of those accumulation functions, and I take the derivative of that accumulation function, okay, we mentioned that an integral is also, we find that by taking antiderivatives. Because integral represents the antiderivative of the function, yes? So if I then take the derivative of an antiderivative, what's going to happen? They undo each other. So I'm just left with whatever's on the inside. So it's a little bit different than like when we take the square root of x squared, I'm just left with x, right? Here it's a function, so you could have more stuff, but same idea, that they are inverses of one another, so they are going to undo one another. Now, the only other thing that we can see is if my top bound is not just an x, so say it's like x squared plus 2, or the square root of x, or something like that. They still undo each other, but now we have to plug in whatever's there, as well as multiply by the derivative of that. And we'll look at some examples. So, there are two types of questions that you can see from this. The first is the one that y'all tend to like. It's very algebraic, and it's just, we're going to plug stuff in. It's very plug and chug. And we'll look at a couple examples of that. The second type, so the plug and chug type are very like multiple choice type questions. Okay, so they're still important. However, the ones that people tend to not do as well on is the second type, which is going to be from graphs. Okay, and those are usually at least one free response question on the AP test. Okay, and so that's like 1/5 of your points from the free response questions. And from that, your free response questions, because they make up 50% of your grade on the AP test, it ends up being quite important that we are okay looking at these graphs. This also happened to be the question that I got to grade on last year's AP test, so don't make me cry like some students did. Now, like, we don't have names, so I don't know who they were. They could have been, from Alaska or Hawaii or Rhode Island or wherever, but some of their calculus skills were not very great. Okay, so like I said, this is the first type, very, very plug and chug. We're just taking a derivative of an integral, but like I said, our derivative and our integral basically undo one another. So then we're just going to, right now I have t squared, so the only difference about here is I'm going to plug in, because this is now a function of x, I'm going to plug in x for my t. And that's my answer. If you wanted to go the long way around, technically you could take the integral So you would take the antiderivative, then you would plug in x, subtract off plugging in 9, but then you would take the derivative of that. So then basically you're just undoing all of the antiderivative work you just did, which is why you get back to the original function that you have. Questions on that? Okay. Alright. On this next one, I have the derivative of pi over 6 to x squared of cosine t dt. So again, we have t's on the inside, so we're going to plug in that top bound. So this time we have a cosine of x squared. But notice that now on top, since I don't just have an x, I have to plug in the x squared, and then we also have to multiply by the derivative of that. So the derivative of x squared is a 2x. So we get 2x cosine of x squared. The biggest thing that people forget on this one is to multiply by the derivative of the top bound. What questions do we have there? So far so good? Like I said, these are give me questions, okay? We should 100% get these ones right on multiple choice, because like I said, they're just very, very plug and chug. Okay, what's our top bound this time?
E to the x.
E to the x, okay? And then I'm plugging in, how many t's do I have in my function? 2. So we have to plug that e to the x into both of those spots. And then what do I also have to do? Multiply by the derivative. What is my derivative of e to the x? E to the x. Okay. Now, if this is a multiple choice question, they are going to simplify that. What is e to the x times e to the x? E to the 2x. And so that would be your final answer. What do we think is probably like a common wrong answer that's probably going to show up on our options? Yeah, where we just combine them as like 2e to the x instead of multiplied, right? That would be if we were adding. Yes, so that's just a basic algebra skill thing, but just be careful when you're simplifying for your multiple choice questions. Questions on that? Yes? No? Maybe so? So far so good? Okay. Now we're gonna look at graphs. Yay! The graphs are fun. So it says let the following be the graph of f of x. Okay, so that's a little f of x. So we've talked about this before, that we need to be really careful about what type of graph we are looking at. This is little f of x. And then it says let big f of x be defined by the following. Big f of x equals, so notice that this is an accumulation function, the function from 0 to x of f of x. We're missing the dx there. Okay, this is really common notation when we're dealing with accumulation functions, okay? Because just like on my other ones, instead of saying d dx of an integral, I could have said let g be this integral, find g prime, right? That's the same thing as taking the derivative. So you're gonna see a function defined as an accumulation function. Okay. Sorry, d dx is missing, as is our initial condition. So for whatever reason it got chopped off there. So let f prime of 0, that's bad. F of 0 equal to. And we've looked at initial conditions before, right? So it's just basically giving us kind of our way to find our C value. Alright, so for our first one, it asks us to find f, big F of -2. Okay, so be careful because it is not asking us to plug in -2 for our little f, because little f of -2 is just 0. That's not our answer though. It's asking us to plug in -2 into our accumulation function. So it's asking us to go from 0 to -2 of f of x dx. Now, the nice thing about most of these graphs is when we're dealing with an accumulation function, it's going to be very geometric, which is what this is, okay? So we're just looking for what does an integral represent.
Area under curve.
Cool, and we are going from 0 to -2. So what do I end up with there? The triangle, okay? Is there anything wrong or kind of wonky about my interval right now though? So going from 0 to -2. Okay, so right now my A value, right, is bigger than my B value. Yes? So yes, we do want to flip them. In order to flip them, what do I have to do? Do we recall? It's one of our integral properties.
Integral becomes negative.
Correct. Okay. Or the other way that we can think about it, right, is technically we were going from 0 to -2. So what direction am I moving? To the left, right? Which is why it's negative direction. Because remember, our negatives for our areas just mean either that I am below the x-axis, but because it's also now a function, it can also mean I'm moving to the left instead of accumulating to the right. So here's a question. If I was moving to the left and below the x-axis, what would we end up being? Positive, right? Because you would have a negative because you're moving to the left and a negative because you're below the x-axis. So your area there would end up being positive. So you would have a negative. Yes? In this case, we don't. It's positive area. So, we did say, though, that that is a triangle. What is our area of a triangle? Cool. So I have 1/2 times, what's my base?
2.
2. What's my height? 4. So what do we get there? Okay. And we had to multiply by a negative? Yes, no, maybe? Okay, now we do have to be careful though, right? Because remember that when we take integrals, because this is now an accumulation function, okay, it's a little bit different than our original FTC. I do have to worry about my initial condition because we started saying that our big F of 0 equals 2, yes? Which means that whenever we take this integral, I also have to add in our initial condition, which is what? We said it was 2. So we get -4 plus 2 gives us -2. Okay, I'm okay with that. Like it's acting as our C value. So we have to add that C or add that 2 to take care of that. Now, on our second one, we're going from 0 to 3 this time. So we are moving in the correct direction. So it's going to be positive. So what type of shape are we dealing with this time?
Trapezoid.
It's a trapezoid. Do we remember our trapezoid formula?
Base 1 times base 2.
Not times. Plus.
Base 1 plus base 2.
Okay, so what's our base 1?
3.
Okay. What's our base 2?
1.
Okay.
Divide by 2.
Times.
Height.
So our height is 4. So what do we get there? 8. Yeah, we okay with that? But then what do we also have to do since we had an f of 0 there? Plus 2. Because we have to take care of our initial and conditional. So we get 10. Now, the nice thing, and the reason why these are called accumulation functions, notice that my last area is going from 0 now all the way till 6. So I'm looking at all of this. Yes? But the reason why it's called accumulation is because do I already know this first area? Yeah, so I don't have to find it again. I'm accumulating. I'm adding to this area of my next two things. Does that make sense? So we don't have to find the stuff that we already know. The only thing you do have to be careful about is, okay, this 10 includes my initial condition. Yes? So we don't want to add another initial condition if I've already added it for this one. Are we with me there? If you used the 8 for this and then found this area and then this area, then yes, you would add your initial condition. But if you're using the 10, don't add the initial condition twice. Does that make sense? Okay. So we have the integral from, we're going 0 to 6 this time, of f of x dx. I'm going to go ahead and use my 10, okay? This is a triangle. What type of area is that going to be? Triangle. It's going to be negative. So I have 1/2, what's our base? 2, what's our height?
2.
Also 2, so what do we get there? But we're going to do what with that 2?
Make it negative.
Subtract it, okay? And then our last teeny tiny triangle there. What's our base? 1. What's our height? 2. So what do we get?
1.
Okay, and it is positive that time, so we are adding. So we get 8 plus 1, which gives us 9. Yes, no, maybe, no. What questions do we have there? Now, the only other thing that we can do with this is basically we can take our accumulation functions a step further. And this is the part that most students struggle with, okay? And that is going back to our derivative relationships, okay? So talking about increasing, decreasing, and concavity. So, same picture, same function. I also need to add in my x. Okay. So notice here that it is asking us where big F of x is increasing. Yes? No, maybe. Okay. But what did we say? How do I know when a function is increasing or decreasing? If I have the original function, right? I don't have the original function here because remember that function that I have graphed is f of x, little f of x. I need information about big f of x. So if I don't want to graph something, so yes, it's when your slope is positive, slope is negative. What have we found in this class that also represents slope?
The derivative being positive. positive.
Ah, okay, so our derivative being positive or negative. Okay, but what is the derivative of big F of x? Huh?
Is it normal f of n?
Mm-hmm. So this is using our fundamental theorem of calculus. If I take the derivative of big F, right, that's taking the derivative of the other side too. If I take the derivative of an integral, remember we just end up with the inside stuff. So I end up with little f of x. Yes, no, maybe. Now, if you have a free response question like this, it is very important that you state that statement. Whatever it says, if it's, G or H or whatever it is, that you know that H prime or big F prime of x equals my inside function. Because that's where the point. One, it's an easy free point, but two, you also miss that point if you don't explicitly say that that's how you got the rest of your information. So we need to state that. Because remember that this graph is little f. So if I just start talking about values, we don't know where we're getting those values from. But now that I know that big F prime equals little f, okay, we said that we know that f of x is increasing when f prime is positive. Well, I have my f prime here is my little f, so that's this graph. So I'm looking for where it's positive. So where is that graph positive?
From -2 to 3.
Anywhere else?
From 5 to 6.
Okay, which means that it is decreasing when it's negative.
From 3 to 4. Or 3 to 5.
Yes, but you also missed one.
From
Negative
-3 to 2.
Okay. And then it asks us about concavity. When is something concave up or concave down?
When the second derivative is positive again.
Okay, or, because I don't have information about the second derivative here.
The first is increasing.
Yeah, so, or my first derivative is increasing, means that I'm going to be concave up, and my first derivative being decreasing, means that we're concave down. So, where is little f increasing?
-2 to 0.
Be careful, this is at -3.
-3.
-3 up until 0. Or else.
6.
Mm-hmm. And then we are concave down when it is decreasing.
3 to 4. Or not 3 to 4.
1 to 4. And we're just going to skip where it's 0, okay? Because we don't necessarily know. It's not doing either one there, so we just don't use that part. Yes, no, maybe? What questions do we have there? So again, none of these things are necessarily hard in the sense that they're super complicated, but it is piecing together a whole bunch of the different stuff that we've covered up until now, right? We're taking together our derivative relationships that we talked about for a semester. We're taking our geometric area under the curve that we've just talked about, and now looking at our accumulation functions as well. So that's 3 big things, squashing them all together, which is why it can be a little bit hard to wrap our heads around. So, then again, we also have to think about this last part. Where does big F of x have relative mins and maxes? So remember, what are my options for relative mins and maxes?
Extrema. Or critical points.
Okay, can we find our critical points by
Where the slope
where the slope
equals 0.
or the, in other words, instead of slope, we would use the derivative. So we're looking at where our derivative equals 0, yes? But what's the derivative of big F? Little f. So we're looking at where little f equals 0. Where do we equal 0 there?
Negative 85.
-2,
3, 5.
3,
5.
and 5. Okay? And then we just need to decide if those are relative mins or relative maxes. So at -2, we are changing from negative to positive, which means that our original function would be changing from decreasing to increasing, so we would have a
Relative min.
minimum there. At 3, we are changing from positive to negative, so we're changing from increasing to decreasing, which would give us a
Relative maximum.
maximum. And then lastly, 5, again, we're changing from decreasing to increasing, so we have another
Minimum.
minimum.